This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. All right, buckle up, folks. Today's discussion dives deep into Meta's latest offering, the Llama 3 Herd of Models. This isn't your average language model. We're talking a family of multilingual, coding-capable, reasoning-savvy, tool-using behemoths. The largest clocks in at a whopping 405 billion parameters. What immediately strikes you about this architecture and its approach?
The sheer scale is impressive, but what's really interesting is their emphasis on three key levers: data, scale, and managing complexity. They haven't chased exotic architectures. Instead, they've meticulously improved data quality and quantity, 15 trillion multilingual tokens, scaled training FLOPs massively, 3.8 by 1025, nearly 50x more than Llama 2, and opted for a relatively simple, stable training pipeline, dense transformer with minor adaptations, SFT, RS, and DPO. This focus on optimization rather than architectural novelty is a significant departure from some other recent approaches.
So they're betting on refinement over revolution. Let's talk data. How do they improve data quality and quantity compared to Llama 2? What were some of the key pre-processing and curation techniques employed?
They significantly increased the dataset size, moving from 1.8T tokens in Llama 2 to 15T in Llama 3, but it's the quality improvements that are fascinating. They implemented sophisticated deduplication at the URL, document, and line levels using techniques like min-hash. They also developed robust safety filters to remove PII and unsafe content, along with model-based quality filtering using Llama 2 itself as a judge to assess the quality of web documents. They even built domain-specific pipelines for code and mathematical reasoning data. The attention to detail and data curation is remarkable.
Model-based quality filtering is clever. Using the previous generation model to assess the new data is a recursive approach that seems very efficient. Let's shift to the training process itself. What were some of the key challenges in scaling the training to this massive scale, and how did they overcome them?
Training a 405B parameter model on 15.6T tokens presents enormous challenges. They used 4D parallelism, a combination of tensor, pipeline, context, and data parallelism, to shard the model across 16,000 GPUs. This required significant optimizations in their collective communication library, NCCLX, addressing issues like batch size constraints in pipeline parallelism, memory imbalance, and computation imbalance. They also had to deal with the sheer scale of hardware failures, implementing robust automation for handling these issues. Their detailed analysis of interruptions and their solutions is a valuable contribution in itself.
The 4D parallelism is impressive, but the reliability and operational challenges at that scale must have been immense. Their discussion of the infrastructure and the 78% hardware-related interruptions is quite revealing. How did they manage to achieve over 90% effective training time despite these issues?
It was a massive undertaking. They focused on reducing job startup and checkpointing times, developing tools for fast diagnosis and problem resolution, and leveraging PyTorch's NCCL flight recorder for efficient issue detection. They also implemented enhanced ECMP routing and deep buffer switches to improve network load balancing and congestion control. The level of engineering sophistication required to manage a training run of this magnitude is truly remarkable.
Let's move on to the post-training phase. They used a multi-round approach involving supervised fine-tuning, SFT, rejection sampling, RS, and direct preference optimization, DPO. What were some of the key innovations or refinements in their post-training strategy?
Their post-training is equally impressive. They refined their reward modeling, incorporating edited responses in addition to chosen and rejected ones. They also made algorithmic modifications to DPO, such as masking formatting tokens and adding an NLL loss term for stability. They developed custom data curation strategies for various capabilities: code, multilingual, reasoning, tool use, long context. using synthetic data generation extensively to augment human annotations. The iterative refinement process with synthetic data generation and human feedback is key to their success.
The detailed breakdown of their data curation and synthetic data generation techniques for code, multilingual support, and reasoning is particularly insightful. And finally, the safety aspects. How do they approach safety, both during pre-training and post-training? What were some of their key findings?
Safety was a major focus. During pre-training, they implemented extensive data cleaning and filtering to remove PII and unsafe content, and they carefully analyzed memorization rates. Post-training involved safety fine-tuning, using adversarial and borderline prompts to balance violation rates and false refusal rates. They also conducted extensive red teaming exercises to identify and mitigate various safety risks across different capabilities. Their release of Llama Guard 3, a system-level safety solution, is a significant contribution to responsible AI development. The depth of their safety analysis is commendable.
The multifaceted approach to safety, from data curation to system-level safeguards, is crucial. Their detailed analysis of the trade-offs between violation rates and false refusal rates, and their use of red teaming, are particularly noteworthy. This discussion has highlighted the impressive scale and sophistication of Llama 3. Thank you.